Today I'm going to be covering gravity and a few main points. So the first main point is it's not like an electric charge, it's always attractive. And it follows an inverse square law. And this law is F, which is the force due to gravity, is equal to the gravitational constant, big G, times mass of the first object, times mass of the second object, divided by r squared, where r is the separation between the objects. G has the value of 6.67 times 10 to the minus 11, and it has units of meters cubed per kilogram per second squared. So if you do an example with this force, if you do it with two people sitting a meter away from each other, G is going to be, F equals G 6.67 times 10 to the minus 11. Assume both the people weigh 70 kilograms, so that's times 70 squared, and divided by the distance between them, which is 1 meter, and that gives you 3.27 times 10 to the minus 7 newtons. Field lines show the direction that a mass would move when it's inside the field. So if you take Earth, for example, all of the field lines are going to be acting towards the centre. So if the field lines are more dense, it means it's going to be a stronger field, and close to the Earth's surface it appears flat, so the field lines are going to be acting downwards. Little g is defined as the force per unit mass. So to find a proper expression for this, you sub in for force what we used up here, so that is gmm over r squared divided by little m, so that can go in there, cancel these, and you find that little g is capital G, capital M over r squared. And because this can be arranged into the form F equals ma, Newton's second law, it means that gravity is a acceleration. Potential energy is defined as the energy possessed by an object due to its position in the field. So if we work out the potential energy for an object, a height h above the Earth's surface, use U as the symbol for potential energy, and it's also the same as work done, so it's the same as force times displacement, so F times x, but the displacement here is the height above Earth, so use h, so U equals F times h. Subbing in the expression for force, you have gmm over r squared times h, and realizing that little g is big G times big M over r squared, this bit, you have that it's gmh. So this is the expression for a object of mass m at a height h above the Earth's surface, or any body, and g is assumed to be constant in this derivation. A more general derivation of the potential energy is U equals the integral of f dot dx. So subbing in the expressions and changing the integration parameter to r, you have g mm over r squared dr. Integrate this and you have minus gmm over r. As r tends to infinity, f is going to tend to 0. So as you're infinitely far away from the mass, the potential is going to be 0. This means that the potential energy is negative when you're close to a body, because gravity has done work to bring the test mass in from infinity to a position r. So if you want to be picky with this, you can have the limits being going from infinity to a distance r, and that's going to be evaluated from these two limits, which is going to be minus, you can factorize that out, and then you have 1 over r, and that's going to be infinite and r, and that is minus gmm, over r, and this is the same result that we had here without the limits. If we want to know what gravitational potential ng looks like as a function of radius from the center, we can draw that as a graph. So that is radius from the center of the planet, and this is gravitational potential energy, so U. And if you have the planet, or half the planet here, it's going to be a constant potential inside, so the line is going to be flat, and then it's going to be an exponential decrease as r increases. You also need to know about equipotentials, and they are defined as a surface where the potential is constant, so you don't need to do any work to move along it. So a good example of this is the surface of the Earth, and they always have the surface is perpendicular to the field lines. So this is an equipotential here, and so is around here. And I hope that was useful. Thanks.